Hey guys, today we're going to take a look at operations with algebraic vectors in R3. So first of all, we've discussed this previously, but remember we can denote these vectors using scalar components. So we could write vector v as vx, vy, vz, just where we're giving these components. We can denote it like that, or alternatively we could use unit vectors, which was vx times vector I plus y times j, and vz times, that's a z, oh, that looked worse than before. Whatever. There we go. Times k. Okay. So these are two ways you can draw it, or you can denote them. The magnitude then, which we'll write as this, is equal to the square root of vx squared plus vy squared plus vz squared. Okay, so we're going to take a look at an example here. We've got a, which is I minus 3j minus 2k. So first of all, we're going to write this in component form. So this is fairly straightforward. You just take those coefficients there and you make those the components. So it's going to be 1, negative 3, and negative 2. Okay. The magnitude of the vector then, so the magnitude of A will be the square root of 1 squared plus negative 3 squared plus negative 2 squared. Okay, which is just equal to root 14. All right. So to draw this becomes a bit of a challenge, of course, drawing on a three-dimensional plane, but remember, don't get your x, y, and z mixed up. It's not where you might be used to them being, so the x comes out, so we come out 1 unit first, and then we will go negative 3 on the y, so I'm just going to extend this, go 1, 2, 3, and then we'll go down 2 on the z, so we'll go 1, 2. So if we do that, it's of course a little challenging to draw, so what we're going to do is we're going to draw a box there, and a box there, and there. Then we'll extend it over here, and then we can say this point to this point is our vector. So that is A. There we go. So make 3D model of your vector. Well, you're more than welcome to do that at home. So we're going to take a look now at the addition of vectors in R3. So this is fairly straightforward. All it is you're just going to add the individual components, just like in two-dimensional space, except that we have a third component. So we've got A plus B. I'm not sure why I did that in black or in blue, which is going to be AX plus BX, AY plus BY, and AZ plus BZ. And whoosh, there we go. Okay. Or alternatively, we can write this using unit vectors. So we've got AX plus BX times I plus AY plus BY times J plus AZ plus BZ times K. There we go. All right. So if we go to do these with some real examples here, we can say that A plus B is equal to, and I'm just going to use component form because I think it's a little bit easier here. So we'll say 4 plus 1, and then we'll have 1 plus 2, whoops, plus 2, and then finally we've got 3 plus 0. So we've got 5, 3, 3. And there we go. All right. So I'm not going to draw that because you can do that on your own. So here we go. So the second one, we've got A plus B. And same thing. We're just going to go through all the different components. We've got the x's there. So we've got -2. Oh, for crying out loud. -2 plus 2. We've got the 5 and the 0. So 5 plus 0. And we've got -1 minus 3. So -1 minus 3. Okay. So that gives us 0, 5, and -4. And there we go. All right. So if we flip over to this one, you can see the same rules apply in subtraction, of course. You just go component by component. We just look at the x's, we look at the y's, we look at the z's. Okay, so if I've got A minus B, it's just going to be AX minus BX, AY minus BY, and AZ minus BZ. Okay. Or alternatively, in using unit vectors, we can say AX minus BX times I plus AX, UY minus BY J plus AZ minus BZ times K. And there we go. All right. So let's just quickly go through this one here. So the difference D, we're just going to go through, and I'm just going to do this with component form because it's a little easier to write out, I think. So I'm going to say that D is equal to, and we'll have 1 minus 1. The J is -1. Whoops. Minus 2. And for our K, you'll notice there is no K in vector A. That just means that that it's a 0 in front of it. So we've got 0 minus -1, which is just +1. Okay, so we're left with 0, -3, and 1. And there we go. Okay, so the magnitude of D, so we will just have the square root of 0 squared plus -3 squared plus 1 squared. Okay. So it's the square root of, square root, so we got 9 and you got 1, so it'd be square root of 10, okay, which can't be reduced. So there you go. All right. So the last thing I want to go over quickly here is the multiplication by a scalar. And so again, it's all the exact same as in 2 dimensions. It's just that you've got a third dimension. So it's not actually any more challenging necessarily. So let me try that again. Okay, so we've got M times A, where M is a vector. It's just going to be M AX. Oops, no, that doesn't go there. M AY and M AZ. Like that. Okay, or alternatively we would have M AX times I plus M AY times J plus M AZ times Z. Or not Z. Okay. There we go. All right, and there we go. And that's it. All right. So I want you to try these next two questions yourselves before class, and we will take them up. Keep in mind, this challenge question is fairly difficult, but I think that you can do it. So give them a whirl, and we will take them up in class. So until next time, go Sabres.